Absolutely, there is life elsewhere, and almost certainly intelligent life. It has to be. The odds are just overwhelming.
Considering the overwhelming odds, it appears highly likely that life exists beyond Earth. Voyager One has served as our quiet emissary to the vastness of space for many years, and it has finally provided a response. Bill Nye believes that the Voyager missions showcase the remarkable curiosity and ingenuity of humanity as they boldly push the limits of exploration and knowledge. For more than 40 years, Voyager One has faithfully transmitted data back to Earth as it explores far-off planets and ventures into interstellar space. After starting as a one-way broadcast, this expedition has finally received a response. What does this signify? Come along as we delve into Voyager One's unsettling response from the depths of outer space. Space exploration for life. In 1977, 2 spacecraft were launched with a purpose to push the boundaries of human ambition and imagination. Voyager 1 and its twin, Voyager 2, were more than simply robots. They were messengers from Earth, delivering humanity's hopes, dreams, and knowledge. Voyager 1, in particular, became a symbol of our yearning to explore the unknown as it set out on a mission beyond our solar system and into the vast, uncharted expanses of interstellar space. The Voyager missions were groundbreaking, not just for the scientific wonders they represented, but also for the profound philosophical concerns they posed. Each spaceship was outfitted with a golden record, which served as a time capsule, including sounds and images depicting the diversity of life and culture on Earth. The records were created to convey the essence of our world to any extraterrestrial beings that may discover the Voyagers in the far future. This audacious act of sending a message to the heavens demonstrated human curiosity and a strong desire to connect with something greater than ourselves. Voyager 1, currently the farthest distant human-made object from Earth, has become a beacon of exploration and discovery. As it moves through the universe, it continues to send back data, providing us with glimpses into previously unknown parts of space. Its journey ushered in a new era of cosmic inquiry, motivated by the need to comprehend our role in the cosmos. As Bill Nye correctly puts it, humanity is on the verge of a revelation, one that could drastically change our understanding of existence. The spirit of discovery exemplified by Voyager 1 serves as a reminder of the enormous potential of human ingenuity and the limitless possibilities that await us. Carl Sagan, a visionary in astronomy and a key member of the Search for Extraterrestrial Intelligence movement, notably claimed that our galaxy alone could contain up to 1 million civilizations. His comments capture the optimism and amazement that fuels the search for life beyond our planet. The vastness of the universe means that the chances of discovering other intelligent species are high, making the hunt for extraterrestrial intelligence a long-term and hopeful endeavor. The search for extraterrestrial life advanced dramatically in the 1960s when astronomers started on an ambitious mission to discover signals from other civilizations. The problem was daunting. How would we communicate over the vast distances between solar systems? 2 principal tactics emerged: direct communication, which required travel across large spans of space, and long-distance transmission, which relied on transmitting and receiving electromagnetic signals. Given the large distances involved, direct communication was deemed unfeasible, making long-distance transmission the more plausible choice. Radio waves, which can travel through space, became the principal means of attempting to communicate with potential extraterrestrial civilizations. This strategy was based on the transmission and receipt of electromagnetic signals, with the hope that another civilization was doing the same. One of the most significant efforts in this direction occurred in 1974, when astronomers at Puerto Rico's Arecibo Observatory transmitted a 200-byte message to the globular star cluster M13. This message, known as the Arecibo message, was a symbolic attempt to signal human presence in the universe. It included information about the molecular structure of DNA, the atomic numbers of essential elements, and other fundamental facts about humanity and our role in the universe. While this deliberate act of communication was daring, it was also unusual. The majority of attempts in the search for alien intelligence have centered on passive listening, hoping to pick up signals from civilizations that may be contacting us. Radio telescopes play an essential part in this passive listening strategy. These gadgets are intended to detect long wavelength energy waves that optical telescopes cannot see. Astronomers can detect signals that may indicate the presence of advanced civilization by directing a big antenna at a star similar to our Sun and tuning it to the microwave region of the electromagnetic spectrum. Flyby of Jupiter. As Voyager One approached Jupiter, anticipation mounted among scientists and space enthusiasts alike. The mission promised to reveal a treasure trove of data, offering insights into a world that had remained largely elusive. The climax of this journey came when Voyager One performed a close flyby of Jupiter, skimming just 300,000 kilometers above the planet's tumultuous atmosphere. This close encounter marked a watershed moment in space exploration, providing humanity with its first detailed look at Jupiter's complex system. In the meticulously planned 48-hour window leading up to the closest approach, Voyager One conducted an exhaustive study of Jupiter, its moons, and its surrounding environment. The spacecraft's instruments were tuned to capture every detail, from the swirling patterns of Jupiter's cloud tops to the dynamic interactions within its vast magnetosphere. This period of intense observation yielded a wealth of data, fundamentally reshaping our understanding of the gas giant and its place in the solar system. One of the most groundbreaking discoveries of the mission was the detection of active volcanism on Io, one of Jupiter's largest moons. This revelation was nothing short of extraordinary, as it marked the first time that active volcanic activity had been observed outside of Earth. The volcanic plumes, spewing sulfur, oxygen, and sodium into space, challenged long-held beliefs about the geological activity of other celestial bodies. The implications of this discovery extended far beyond itself, offering new perspectives on the processes that drive planetary systems. The interaction between the volcanic output and Jupiter's magnetic field uncovered complex dynamics that were previously unknown. Jupiter's magnetosphere, influenced by the planet's immense magnetic field, is one of the most powerful in the solar system. The data collected by Voyager One revealed how the volcanic emissions were intricately linked to the behavior of Jupiter's magnetosphere, shaping its structure and influencing the planet's radiation environment. Voyager One's flyby also unveiled another surprising feature of Jupiter: its faint but unmistakable ring system. Unlike the prominent rings of Saturn, Jupiter's rings are delicate and elusive, consisting primarily of tiny particles that reflect very little light. The discovery of these rings was a revelation, prompting astronomers to reconsider their understanding of ring systems across the solar system. It became clear that rings were not a unique characteristic of Saturn, but a more common feature that could exist around other planets as well. The images captured by Voyager One of Jupiter's Great Red Spot, an enormous, centuries-old storm, were equally significant. These detailed observations provided new insights into the storm's structure and dynamics, offering clues about the atmospheric processes that sustain such a massive and long-lived phenomenon. Understanding the Great Red Spot has had far-reaching implications, influencing models of atmospheric behavior not only on Jupiter, but also on other gas giants and even on Earth. Flyby of Saturn. On November 12, 1980, Voyager One achieved a milestone in space exploration as it soared to within 100,000 kilometers of Saturn's cloud tops. This historic encounter was the result of years of anticipation and meticulous planning, as the spacecraft's sophisticated instruments were poised to reveal the secrets of Saturn, the ringed giant of our solar system. As Voyager One closed in on its target, it began transmitting stunning images back to Earth, capturing the awe-inspiring complexity of Saturn's rings and offering a glimpse into the planet's enigmatic interior. The first revelations came in the form of breathtaking images of Saturn's rings. What had long been assumed to be simple, static structures were shown to be anything but. The photos revealed a mesmerizing dance of icy particles and rocky debris swirling together in an intricate and ever-changing gravitational ballet. These rings, once thought to be uniform, were, in fact, dynamic systems, their structure constantly shifting in response to Saturn's powerful gravitational forces. This discovery not only captivated the public, but also challenged scientists to rethink their understanding of planetary ring systems. As Voyager One continued its journey, its advanced instruments delved deeper into Saturn's atmosphere, uncovering a world dominated by hydrogen. The spacecraft's sensors detected a surprisingly low concentration of helium in Saturn's upper atmosphere, just 7% compared to the 11% found in Jupiter's atmosphere. This discrepancy raised intriguing questions about Saturn's internal dynamics and energy balance. Scientists speculated that helium, being denser than hydrogen, might be sinking deeper into Saturn's atmosphere, contributing to the planet's excess heat output compared to the energy it receives from the Sun. Voyager 1's exploration of Saturn's atmosphere also revealed extraordinary weather patterns. Near the equator, winds roared at incredible speeds, exceeding 500 miles per hour, with the majority of these fierce gusts moving eastward. These winds, reminiscent of the powerful jet streams found on Jupiter, suggested a turbulent atmospheric system driven by immense internal forces and solar heating. The spacecraft also captured evidence of auroral displays on Saturn, similar to Earth's northern and southern lights, but with a unique twist. Ultraviolet emissions from hydrogen at mid-latitudes hinted at complex chemical reactions occurring high in Saturn's atmosphere. Additionally, auroras were observed in the polar regions, caused by energetic particles from the Sun interacting with Saturn's magnetic field. These auroral events suggested the formation of complex hydrocarbon molecules, which were then transported from the poles toward the equator, highlighting the dynamic interplay between Saturn's magnetic environment and atmospheric chemistry. One of the most eagerly anticipated moments of Voyager 1's mission was its close encounter with Titan, Saturn's largest moon. Titan. Voyager 1's approach took it to within 6,400 kilometers of Titan's surface, allowing the spacecraft to gather unprecedented data on this mysterious moon. Despite the thick haze that shrouded Titan, Voyager 1's instruments were able to analyze its atmosphere, revealing that it was composed primarily of nitrogen, with significant amounts of methane and other hydrocarbons. These findings supported the hypothesis that Titan might harbor lakes or seas of liquid hydrocarbons beneath its opaque atmosphere, a tantalizing possibility that would drive future exploration and research. Journey beyond the solar system. On February 14, 1990, Voyager 1 accomplished something extraordinary. It captured the first-ever family portrait of our solar system from a vantage point beyond its outermost planets. Among the images taken was the now iconic pale blue dot, showing Earth as a tiny speck amidst the vastness of space. This profound image serves as a powerful reminder of our planet's fragility and our place in the universe. Shortly after this historic photo was taken, Voyager 1's cameras were turned off to conserve power for other critical scientific instruments on board. The decision to deactivate the cameras marked the end of an era, as the spacecraft's imaging software was deleted, making it impossible to take any more pictures. Additionally, the equipment on Earth needed to interpret these images had become obsolete, further cementing this image as a lasting record of Voyager's mission. Just 3 days later, on February 17, 1990, Voyager 1 surpassed Pioneer 10, becoming the most distant human-made object from Earth, at a staggering distance of 69 astronomical units from the Sun. Traveling at a remarkable speed of 17 kilometers per second, Voyager 1 holds the record for the fastest heliocentric recession velocity of any spacecraft launched from Earth. Even as it ventured farther into the outer reaches of our solar system, Voyager 1 continued to collect invaluable data. The spacecraft's instruments, meticulously designed for long-term operation in the harsh conditions of space, provided scientists with critical information about the Sun's influence at the farthest edges of its reach. One of the essential experiments aboard Voyager 1 was the plasma wave experiment, which NASA's Jet Propulsion Laboratory used to study the heliopause, the boundary where the solar wind meets the interstellar medium. Understanding this boundary is crucial for comprehending how the Sun interacts with the broader cosmos beyond its direct influence. By 2013, Voyager One had reached an astonishing relative velocity of about 60,000 kilometers per hour with respect to the Sun, traveling approximately 523 million kilometers annually, roughly the equivalent of 1 light year every 18,000 years. These numbers underscore Voyager One's role as humanity's pioneering ambassador, hurtling through the cosmos at unimaginable speeds. As Voyager One approached the outer boundaries of our solar system, the scientific community became embroiled in a heated debate about its journey. Researchers at the Johns Hopkins University Applied Physics Laboratory suggested that Voyager One had crossed the termination shock in February 2003. The termination shock is a critical boundary where the solar wind slows down to subsonic speeds, marking a significant transition in the spacecraft's journey. If confirmed, this crossing would represent a monumental milestone in Voyager's mission, indicating its entry into a region where the dynamics of the Sun's influence change dramatically. However, this claim was met with skepticism. In November 2003, the issue of the journal Nature, some scientists questioned the validity of Voyager One's supposed crossing of the termination shock. Their doubts stemmed from the fact that Voyager One's solar wind detector had failed in 1990, making it difficult to directly observe the termination shock. Without this crucial instrument, scientists had to rely on indirect data, which introduced uncertainties and made interpretation challenging. This debate persisted, highlighting the complexities of space exploration and the challenges posed by aging spacecraft instruments. In May 2005, NASA issued a press release indicating a provisional consensus among scientists that Voyager One had indeed entered a region known as the heliosheath. This announcement came after a significant scientific meeting at the American Geophysical Union in New Orleans in May 2005. Ed Stone, a prominent figure in the Voyager mission, presented compelling evidence suggesting that Voyager One had crossed the termination shock in late 2004. Unraveling the mysteries of the cosmos. In March 2006, a groundbreaking event occurred that forever changed the landscape of amateur radio astronomy. A group of dedicated enthusiasts from AMSAT in Germany accomplished what many believed was impossible. They tracked and received radio signals from the Voyager One spacecraft using a modest 20-meter dish antenna near Bochum. This remarkable feat, the first of its kind, demonstrated not only the technological prowess of amateur astronomers, but also their unyielding passion for deep space exploration. This extraordinary achievement resonated far beyond the amateur radio community, drawing the attention of professional scientists and astronomers worldwide. The signals intercepted by the German team were meticulously cross-referenced with the precise records held by the Deep Space Network Station in Madrid, Spain. The results were astonishing. The amateur astronomers' findings were validated as legitimate and accurate, confirming that they had successfully intercepted communications from a spacecraft billions of kilometers away. This validation was more than just a technical success. It was a testament to the power of collaboration and innovation within the global amateur radio community. It also provided crucial information about Voyager One's ongoing journey beyond our solar system, adding a new layer of understanding to its mission. The event marked a significant milestone in the history of space exploration, proving that even those without access to the resources of a space agency could contribute meaningfully to humanity's quest to understand the cosmos. Voyager One's journey, however, was far from over. In December 2010, the spacecraft reached another historic milestone. It was confirmed that Voyager One had crossed a boundary where the radial outward flow of solar wind from the Sun had ceased, marking its entry into a new region where the Sun's influence was diminishing. This discovery, made possible by data from Voyager One's low-energy charged particle instrument, revealed a profound shift in solar wind behavior at the spacecraft's location, which was approximately 116 astronomical units, or about 18 billion kilometers, from the Sun. This distance was more than just a number. It signified Voyager One's entry into interstellar space, a region where the solar wind is overpowered by the interstellar wind. The absence of detectable solar wind since June 2010 was a clear indication that Voyager One had crossed the heliopause, the theoretical boundary where the Sun's influence wanes, and the interstellar medium begins. This observation aligned with scientific expectations about the outer edges of the heliosphere, offering a rare glimpse into the uncharted territories of space that lie beyond our solar system. In March 2011, Voyager One executed a carefully planned maneuver to further explore its new environment. This maneuver was a significant departure from its original mission trajectory, which had been focused on capturing the iconic family portrait of the solar system in 1990. The spacecraft reoriented itself, performing a precise 70-degree counterclockwise roll relative to Earth. This reorientation was not a mere adjustment. It was a calculated move to measure the lateral velocity of the solar wind, providing valuable data about the dynamics of this transitional region between our solar system and interstellar space. Despite this significant maneuver, Voyager One remained aligned with its guiding star, Alpha Centauri, a symbol of its steadfast journey through the cosmos. As the spacecraft continued to relay vital data back to Earth, its astronomical coordinates kept it within the constellation Ophiuchus, a reminder of its solitary voyage through the vastness of space. The surprises didn't end there. In December 2011, Voyager One made another groundbreaking discovery when it detected Lyman alpha radiation from the Milky Way galaxy. This type of radiation, previously observed only in distant galaxies, had been elusive within our own galaxy due to interference from the Sun. The successful detection of Lyman alpha radiation by Voyager One represented a significant leap forward in astrophysics, offering new insights into the cosmic environment surrounding our solar system. As if these discoveries were not remarkable enough, December 2011 brought yet another revelation from Voyager One. NASA announced that the spacecraft had entered a region described as a cosmic purgatory. This zone, a kind of transitional area between the heliosphere and interstellar space, was characterized by a dramatic slowdown and change in the direction of charged particles from the Sun. Simultaneously, the solar system's magnetic field grew stronger under the pressure of interstellar forces. In this mysterious region, Voyager One observed a nearly 50% reduction in the energetic particles that originated within the solar system. Even more astonishing was the 100-fold increase in high-energy electrons coming from beyond our solar system. Signals from the stars. On a warm August night in 1997, the Ohio State University Radio Observatory, affectionately known as Big Ear, picked up an extraordinary signal while scanning the cosmos for extraterrestrial transmissions. This signal, which was 30 times louder than the usual hum of space, lasted a brief but electrifying 72 seconds. It was a moment in time that would leave astronomers both baffled and mesmerized, sparking curiosity and debate that continues to this day. The signal was discovered by Jerry Amon, a volunteer at the observatory, as he sifted through data from the past 3 days. What he found was a sequence of letters and numbers that stood out against the backdrop of ordinary noise. It was so striking that he hastily scribbled "wow" on the printout, a word that would become the unofficial name for this enigmatic event. The "wow" signal, as it came to be known, had a frequency that almost perfectly matched the electromagnetic wavelength of hydrogen, the most abundant element in the universe. This led the SETI, also known as the Search for Extraterrestrial Intelligence Team, to believe that this frequency might be an ideal channel for interstellar communication. The signal's form, when plotted against time, painted a compelling picture. It started at a modest 6 on the telescope's intensity scale, peaked at a dramatic U, and then tapered off, a symmetrical pyramid-shaped curve that hinted at something beyond the ordinary. The implications were staggering. A signal of this nature, with its restricted bandwidth and precise structure, suggested an origin far beyond the reach of natural phenomena. It hinted at the possibility of an artificial transmitter, perhaps a message from an intelligent civilization light years away. Yet, despite the excitement, the signal's origin remained a mystery. Was it a reflection of a terrestrial radio wave bouncing off space debris? A secret communication from a hidden military satellite? Or something more extraordinary, a message from another world? Despite numerous theories, the trustworthy source of the WOW. The signal has never been identified, and it has not been detected since. Its fleeting nature and the inability to replicate it have left experts puzzled, and the WOW signal remains one of the most compelling pieces of evidence in the ongoing search for alien life. Challenges. For decades, Voyager One had been a silent emissary, representing humanity's quest to explore the mysteries of the universe. But now, its transmissions had taken a strange turn, and NASA's Jet Propulsion Laboratory was at a loss to explain the sudden anomaly. The signals, though steady, were garbled and filled with mysterious and peculiar data that baffled even the most seasoned engineers. The source of the problem was traced back to Voyager One's attitude articulation and control system, a critical component responsible for maintaining the spacecraft's orientation as it traveled through the cosmos. Even more puzzling was the discovery that this distorted data was being sent through a computer that had been dormant for years. How could a long-defunct system suddenly spring to life and interfere with Voyager's mission? As the days turned into weeks, the mystery deepened. The spacecraft, which had been launched in 1977, was operating far beyond its intended lifespan. The hardware on board was outdated, and the software had been designed in an era when computers were the size of rooms. Yet, Voyager One had defied the odds, continuing to send back valuable scientific data as it journeyed through the outer reaches of our solar system and into interstellar space. The situation grew more urgent as the garbled signals persisted. Engineers at JPL knew they had to act quickly to prevent further damage to Voyager's systems. Over the next 3 months, they painstakingly analyzed the data, running countless simulations and tests in an attempt to identify the root cause of the problem. Finally, in August 2022, a breakthrough was made. The team managed to reprogram the attitude articulation and control system to bypass the malfunctioning computer and use a functional one instead. The fix appeared to work, stabilizing the spacecraft and allowing it to continue its mission. However, the underlying cause of the computer's unexpected activity remained a mystery. Theories ranged from high-energy particles interfering with the electronics to simple wear and tear after decades in space. But one thing was clear: Voyager One's resilience was a testament to the ingenuity of its creators and the enduring spirit of exploration that drove them. The respite was short-lived. In November 2023, Voyager One once again began transmitting incomprehensible data. This time, the issue was even more severe. By December, NASA announced that the spacecraft's flight data system could no longer communicate with its telemetry modulation unit, a critical component for sending scientific data back to Earth. Without this link, the flow of information that had been Voyager One's lifeblood was cut off. The engineers faced a daunting challenge. Months of meticulous investigation followed as the team sifted through the jumbled transmissions in search of clues. By March 2024, progress had been made. The culprit appeared to be a memory bank, likely damaged by cosmic radiation or simply aged beyond its functional limit. This failure had caused the telemetry modulation unit to loop endlessly, sending out a barrage of meaningless data that confounded the team's efforts to regain control. Despite these setbacks, the Voyager One mission was far from over. The spacecraft continued to respond to commands from Earth, its carrier tone a reassuring signal that it was still operational. Engineers seized on this lifeline, devising innovative methods to bypass the damaged memory banks. By April 2024, they had rewritten the spacecraft's code, allowing it to restore communications with Earth at the cost of losing some non-essential capabilities, including historical data from earlier phases of the mission. The success was bittersweet but significant. NASA announced that Voyager One had resumed transmitting scientific data from 2 of its 4 remaining instruments. It was a victory won through persistence and creativity, showcasing the determination of the engineers to overcome the formidable challenges posed by a spacecraft operating in the harshest environment imaginable. By June 2024, all 4 instruments were back online, and Voyager One was once again fulfilling its mission to explore the furthest reaches of our solar system and beyond. Message to the cosmos. The Voyager Golden Records, carried by Voyagers 1 and 2, are humanity's cosmic time capsules designed to tell the story of our planet to extraterrestrial civilizations. These phonograph records depict a rich tapestry of Earth's diversity, including greetings in 55 languages, music from various cultures and eras, and natural sounds such as whale calls and rainfall. They also include a map of Earth's position in the galaxy, marked by 14 pulsars with different periods, which could serve as a guide for any intelligent beings who discover them. However, the disclosure of Earth's coordinates has sparked debate among scientists and the general public. While some see it as a bold step towards potential contact with advanced extraterrestrial civilizations, others warn of the risks. The fear is that revealing our position will attract hostile aliens, a theme commonly explored in science fiction. For example, L. Ron Hubbard's Battlefield Earth depicts a scenario in which Earth's signals lead to an alien invasion. Though fictional, such stories express genuine concerns about the dangers of exposing ourselves to unknown cosmic entities. The debate continues as we consider whether the benefits of interstellar communication outweigh the potential drawbacks. Thanks for watching. See you again soon.